Okay, so hello everyone. Today our group will present to you guys about a very interesting topic and a very interesting data structure, and it is the Fenwick tree, or some of you may hear about the binary indexed tree. And so our group is the group number 7. Okay, so here's the table of contents. First of all, I will introduce to you guys about this tree, then about the binary and algorithm, demo and applications, quizzes, and finally the exercises that you can participate in. So first of all, I will introduce about the problem and the naive solution that is related to this Fenwick tree, the historical background, and finally the insights and the key ideas of this data structure. So about the problem, we know that these days in many applications, we need to compute the prefix sums or the range sums. So especially you guys, some of you may participate in the competitive programming. You should understand that the technique prefix sums is a very efficient way. However, um, sometimes we need to perform the updates or the query frequently on the array elements. So here is the example of the prefixum. Uh, so uh, rec- uh, so regarding the updating and the querying to this array, what we need to think about the most is the performance. So the naive solution of doing finding the sum of the array is by creating the prefix sum. So you guys will compute the sum from the index 1 to k. So then the time complexity of this action is on. For the update operation, we modify the elements directly in the array, so the time complexity is very low, which is only O1. However, the limitations of this approach is when many updates and many queries is implemented, we will have this trade-off. The faster the query, the slower the update, or the faster the update, the slower query. So we may think about a solution that could handle this issue both efficiently, and that is when the Fenwick tree comes to life. So let's talk about the historical background of the Fenwick tree. It is introduced by Peter M. Fenwick, an honorary associate professor at the University of Auckland, New Zealand. His specialty is in data compression, and the Fenwick tree is published in the paper A New Data Structure for Cumulative Frequency Tables in 1974. The key insights of the Fenwick tree is that Fenwick realized that we can store the partial sums strategically. It means that if you want to store the sum of element 1 to element n, you can store them into like element 1 to element k and element k to element m. And then if you want to find the whole sum of element 1 to n, you can get the sum of the two subsum. And the idea is that he realized that any integer can be represented as a sum of powers of 2. So it is basically the binary number. So he thinks that this approach may lead to the efficient updates and queries. So let's talk about the Fenwick tree. What is the Fenwick tree? A Fenwick tree, or the binary index tree, is a data structure for managing the prefix sums, implemented using an array. It supports the point of updates, the prefix sum queries, and the most prominent features of this data structure is that the time complexity of updating is O log n, and the query is also O log n. So it is like this is a very fair trade-off. The key ideas of the Fenwick tree. The first one, let's talk about the core concept. The core concept is that each index in the Fenwick tree stores the sum of a specific range. The range size depends on the lowest set bit of the index. And the approach of the Fenwick tree is the binary insight. It uses the binary representation of the index of each node in the tree. So instead of scanning the whole array, we only visit the log n nodes. So next one is about the binary and algorithm, and I will introduce my teammates to continue the presentation.
Yeah, like picture, binary, and algorithm. We will draw to three parts: base manipulation, algorithm of bit, and complexity. Okay, first we look at bit operators. On this slide, we look at the base yn, and as you can see in the table, we compare each pair of bits from x from y. The result is 1 only when the both bits are 1. Otherwise, it's ER. You can see. And for example, 8 equal 10 is the and y equal 11 in binary. For so when we apply n, we compare bits and bits and get the result 10. This is similar to the logical and get, you can see, where the output is 1 only if both input are 1. Next, mm, next is the bitwise not operator. This operator fails a bit. That means 0 become 1 and return. It means 1 become 0. For example, if we have a binary number of line, not will result on bit. You can see 0, 0, 0, 0, 0, 1, 0, 0. And I apply bitwise complement 1, 1, 0, 1, 0 to 1, 0 to 1, and only 1 to 0. So you can see um, not for E here. But remember the first bit in binary number is the sign of number. It, for example, is 0. It means the number is positive and 1 is either negative. So it's equal 1, 2, 3, 4, 5, 6, 7, 8. It's the power of 7 times minus 1. Okay, now we move to the main problem. We want to calculate sum efficiently. So instead of computing from step every time, I can we store sum of small segment and resume them? Um, yeah, and idea is similar to segment tree. You remember segment tree in uh, yeah, where we divide into smaller parts. But here we don't split arbitrarily. Instead, we try to cover prefix using predefined block. This means this helps avoid recomposing and makes operator faster. Okay, later. Um, for our I, we then always access a block. You can see, and this means it index store in some of the specific blocks ending is at I. So instead of storing individual value, we store partial sum that can be combined later. Um, and so you can see, um, maximum divisor and power of 2 is in the least significant speed, LSB. Yeah, and remember plus 1 in comparison Y. Okay, next, we look at the visual example. Here we present number like 6 and 7 in binary form. By looking at the binary structure, we can see the segment are determined. The important idea is the last set bit control inside of the segment. You can see the number 6 manager 2. It means it's a array 6 plus array 5. Yeah. Okay, this slide continue the visualization. It have understand how to different index comparisons and different block size, how how their block can be combined to from preface. So you can see, remember, sick and this is right, fine and sick. See here, sick. This is sick and fine. Sick. And actually, I have two-way visual example, and this uh similar is either tree. This is tree. So and next, I will introduce you functions get function. This function is used to calculate the prefix sum. For example, we want to compute the sum from A1 to A30. Instead of summing all elements, we jump between blocks and add their storage value. Okay, next, let's see. We have A. Um, we need to calculate A1 plus A2, A3, A4 from there to A13, right? So we only put bit 30 plus bit 12 and plus bit 8 because the bit 8 contain the 1, 2, 3, 4, 5, 6, 7, right? And bit 12 contain 9, 10, 11. Oh, so it's very amazing. You understand? Okay, here this is the code for get function. This code repeatedly move backward using bit operation and accumulate the results from different segments. You see index and next index is index minus this is list as sorry LSB, right? This is here list significant bit. Yeah, and we'll stand here neck and neck. Okay, it's easy. Neck. This neck function is very important. This update function. What update function? When we increase a value from example A13, we increase A13's amount data it. Sorry, data act. And you know, the bit content content A13 is affected. So we need to update not only that position, but also on segment that includes it. Okay, so this code 2, and this is the code for the update function. You can see, I make actually parents is similar to index in code 1. So parent to you remember it means I will stand here. I stand here and neck. I will stand here and neck. You understand? And neck. Actually, I only go to the 60 because 16 is um no number only. Yeah, and this is on. I want to ask you. Remember the complexity term is either log log n because you know the it is similar the binary search tree. You divide this power of 2 and divide this, and it's the logarithm of 2 and this is the logarithm of 10. Yeah, thank you.
So next we will start with the third part, which is demo and application of Fenwick Tree. In this part I will cover three topics. The first one is the step-by-step demonstration. The second is the applications of Fenwick Tree, and the third one is the dataset in real life and also a comparison between the data structures. So, first of all, we will start with the step-by-step demonstration. Here I use a one-index initial array, which includes, as you can see, 9 elements: 0, 3, 2, -1, 6, 5, 4, -3, and 3. And the bit array here is all 0. With phase 1, the build, there's the golden rule when working with Fenwick Tree, which is the number of elements in node manages equals its lowest set bit, LSB. To understand more about this, I have here 4 examples. With index 1, which is 001 in binary, its LSB is 1, and so bit 1 manages only one element, just itself, the A1. With index 2, which is 010 in binary, its LSB is number 1 here, which is 2, so bit 2 manages 2 elements, A1 and A2. Index 4 has the LSB 4, and this corresponds to the fact that bit 4 manages 4 elements from A1 to A4. And with index 8, 1000 in binary, its LSB is 8, which means that bit A will manage all 8 elements, 81 to 88. And to build the bit array used for a specific array, instead of calling updates n times for each of the slots in the bit array, we can build the tree in only on time with the following steps. First step is to copy the array into bits. With this line, you can see bits is equal to r. And the second step is to let every node passes its total to its parent node if the parent exists. For example, with index 1, its LSB is 1, so its parent will be 1 plus 1, which is 2. With index 2, which is 010, its LSB is 2, so we find a parent which is 2 plus 2, which is 4. We update 4. And also, with the last 4 indexed, which is 100 in binary, we can see that its LSB is number 1 here, which is 4. So its parent is 4 plus 4, which is 8. The code here is quite straightforward. We build from 1 to n. We first find the parent by taking I plus the bitwise AND operator between I and minus I. And if the parent is still in the range considered, then bit parent will be plus by an amount equal to bit I. We come to the second phase, which is the query. At this phase, I represent 3 of the most popular queries when working with Fenwick Tree. The first one is calculate the sum of elements from 1 to n. In here, I let n equal to 7, and we get the function getSum7. The second query is to calculate the sum of elements in a range. And at here, I choose that range is from index 4 to 7, which is range sum for 7. And the last query I'd like to discuss is to update an element in the bit array. Specifically, it is increase the third element by 2. With getSum7, we will start at index 7, and we constantly collect the value and subtract the LSB to find the next puzzle piece, which is its son, its child. We can chase here. We start at 7, which is 111 in binary. So obviously the LSB is 1. We take bit 7 and we jump 7 minus 1 is 6. Next we move to 6, which is 110 in binary. Its LSB is 2. So we take bit 6 into the result and we jump 6 minus 2 is 4. Finally we move to 4, 100 in binary. Its LSB is 4, so we take bit 4 into the result, and then we have covered successfully from A1 to A7. Now, the final jump 4 minus 4 is 0, which is out of bound, since the array we use is 1 indexed. So we finish here. The code represents the idea. We let the index equal P, and the result at the start is 0. While the index is still in the range, we let the result to plus the bit of the index, and then we update the index to its child. The second type of query is range sum, and at here we utilize the property of prefix sum. it's obvious that when we call getSum7, we get the result from A1 plus A2 plus etc. until A7. Similarly, getSum3 returns the sum of A1 and A2 and A3. So if we subtract the two, getSum7 and getSum3, we get the perfect result we'd like to have. That is A4 plus A5 plus A6 plus A7. And so the code for the sum range is pretty straightforward. We just return getSum R minus getSum L minus 1. The last type of query I'd like to introduce is the update query. And here we'd like to increase A3 by 2. So we will have to start at index 3 for sure. And then we add the value. We constantly also add the LSB to notify every ancestor of the chain. Let's trace this. We start at 3, which is 0, 1, 1 in binary. The LSB is 1. So we add 2 to bit 3, and we jump 3 minus 1 is 4. Now we move to 4, which is 100 in binary. Its LSB is obviously 4. So we add 2 to bit 4, and then we jump 4 plus 4 is 8. Now we move to 8, which is 1000 in binary. Its LSB is 8. So we add 2 to bit 8 and we make the final jump. 8 plus 8 is 16. This is obviously out of bounds, since our array is indexed from 1 to 9. Code here represents the idea clearly. We start with index p, and while index is still in the range from 1 to n, we let bit at the index element plus an amount equal to x, and then we update index to its ancestor. The next part is the applications of Fenwick Tree. The first and most obviously seen application is competitive programming. Fenwick Tree is a very popular data structure used in competitive programming because of 3 reasons. The first is implementation speed. Competitive programmers can set up Fenwick Tree super fast. It only requires some lines of coding and some auxiliary functions such as getSum or update. The second benefit of using Fenwick Tree is its memory limit, since it only uses an array of exactly n elements. And last but not least, the raw performance of Fenwick Tree is what most competitive programmers trust. It runs really fast due to its reliance on bitwise operations and array lookups. Another application of Fenwick Tree is in data compression algorithms, known as arithmetic coding. Here, Fenwick Tree helps managing changing data probabilities. Arithmetic coding always need to maintain a dynamic frequency table of characters, and by using Fenwick Tree, arithmetic coding can update these character frequencies and calculate the cumulative probabilities for the compression math in O log n time, keeping the compression process blazing fast. As you can see here, by using Fenwick Tree, one can access and update and also calculate the sum of the probabilities blazing fast. Fenwick Tree is applied into many fields, but here I only introduce 2 more because of the scope of this seminar. The first application is machine learning and genetic algorithms, namely roulette wheel selection. In this field, Fenwick Tree is used along with binary search, and with this combo, AI can instantly pick the right candidate for the genetic algorithm. The next application is video game leaderboards and matchmaking. Here, game programmers use bit to store the frequency of scores, and by using bit, one doesn't need to sort the entire database. We simply find the rank of the players by using bits, and it will return in only O log n time. The last subpart of demo and application is dataset and comparison. The dataset I choose is Bitcoin historical data from 2010 to 2024. And here, the file contains detailed record of Bitcoin's daily price movement. And based on this file, I will have two main queries: update and calculate sum in a range. Definitely I will use Fenwick Tree for these queries. And here are two graphs represented two types of queries. The first graph is 100% queries are range sums. And with this graph, we can see that the naive array is the slowest because it has to calculate every element contained in the sum. The Fenwick tree will stand in the middle, whereas the prefix sums will cause the fastest time because this is its characteristic. And with the second type, update queries, I wrote 100% of queries as updates, and we can see that prefix sums are the slowest. Its time skyrocketed because when updating an element, prefix sums also have to update every element above it. With naive array, updating is super fast since it only has to access an element and make some algorithms at that element. Fenwick tree is a bit slower than naive array. When mixing these two queries together, a half updates and a half range sums, we get this graph. Prefix sums still are the slowest, and naive array comes next. Fenwick tree here represented the fastest data structure when implemented in an environment with a lot type of queries like this. To sum up, we have this table of comparison between various data structures' performance. Notice how the four data structures represented here, naive array, prefix sum array, Fenwick tree, and segment tree, all have a build time of ON. With updating query, naive array is 01 because it can easily access an element. Prefix sum array, on the other hand, costs ON time because when updating an element in this array, we also have to update all elements up above it to maintain the characteristic of the prefix sum. Both the Fenwick tree and the segment tree share the same time for updating and range query, which is O log n. In this query, the prefix sum array only codes ON 01, whereas the naive array codes ON. And for the space complexity, the first three data structures share the same space, which is ON. But segment tree, it requires approximately 04n space. When discussing about the difficulty of implementing these data structures, one can easily implement naive array and prefix sum array. Fenwick tree is not too hard to implement, it's just quite abstract, but it's really short. The segment tree is considered hard to implement because it is long and also use recursive. And so based on this table, we can see that Fenwick tree can easily be the best choice of competitive programmers, providing its benefits here.
So now we will go through some quizzes to review everybody's knowledge about the Fenwick tree that is presented in the previous slides. So the first question is, what is the time complexity for both the update and query operations in a Fenwick tree with n elements? And the answer is C, O log n. So because in an array of size n, all indices have at most log n set bits, so updates and query operations only take logarithmic time. And for question number 2, if you have a Fenwick tree that provides prefix sums, pre-k equals a1 plus a2 plus etc plus ak, how do you calculate the sum of elements with index in range L to R? And the answer is B, pre or minus pre L minus 1. And this is explanation for this problem. So sum of range LR will be equal to AL plus AL plus 1 plus etc. plus AR. So we will add and subtract from this equation the term A1 plus A2 plus etc. plus AL minus 1. And then we subtract it. So the first term will be A1 plus A2 plus etc. plus AL minus 1 plus AL plus etc. plus AR. This term will be pre-R by this definition, and the second term will be pre-L minus 1. And we will come to question number 3. Which of the following is not mentioned in the slides as a primary application of a binary index tree? So if you have attended all the slides before, you will see that answer A, B, and D are already mentioned in the slides. So only C is the one that is not mentioned. And for further explanation, Fenwick Tree only performs with prefix and range sums and updates, not for sorting any datasets. And question number 4, which bitwise operation is used to find the least significant bit to traverse the tree? So the answer is B, x and minus x. And to get minus x, we invert all bits of x and then add 1 to it. And then to get the least significant bit, we perform the AND operation on x and minus x. And for question number 5, what is the number of elements a specific node with index k in the bits manages? And the answer is B, the number of elements equals its lowest set bit. And we will come to the final part, which is the coding exercises. We will have some exercises so that everyone can practice at home. The first problem is LeetCode 307 range sum query mutable 1. Give an integer array nums, handle multiple queries of the following types. Update the value of an element in nums. And then we calculate the sum of elements of nums between indices left and right, where left is smaller or equal to right. When void update with parameter index and val is called, update nums index to be val. And the function sumRange with parameter left and right will return the sum of elements of nums between indices left and right. For example, nums left plus etc. to nums right. We have 2 hints for this one. So think of how much is added or distracted from a range sum if one element is replaced by another value. And the second hint is, if we use the normal prefix sums approach, it will take O(n) some complexity, which will lead to exceeding time limits. So what data structures can help resolve this? And to classify my explanation for instruction, we will have one example. We are given the array nums with value 1, 3, and 5. First, we called the function update 0, 0. So the nums with index 0 is now to be updated to 0, and the array is now 0, 3, 5. And we called the function sumRange 0, 2. So that means we will take all the sums of indices from 0 to 2, which is 0 plus 3 plus 5 equals 8. And then we update to 1, and the nums array will be 0, 3, and 1. We call function sumRange 1, 2. We will take the sum of 3 and 1, which is equal to 4. And the output that we wanted is 8 and 4. For the second problem, which is count number of teams, there are n soldiers standing in a line. Each soldier is assigned a unique rating value. You have to form a team of 3 soldiers amongst them under the following rules. Choose 3 soldiers with index I, j, and k with rating I, j, and rating k. And a team is valid if the rating is sorted in increasing or descending order strictly. So when a team IJK is formed, you are looking for triplets of soldiers based on their positions and ratings. It means that the order of the soldiers in the line is fixed by their indices IJK, so you cannot reorder them to make a team. And a team is valid if the ratings are strictly increasing or decreasing. If you choose, I have a hint for you guys to do this problem. If you choose a soldier J to be the center of the team, how many soldiers to the left are smaller and how many to the right are larger? And for the second case, you only have to do the opposite way. And finally, you will return the total number of valid teams that you can form. We will have two examples to classify my explanation. In example number 1, we will have the rating array, which is with value 2, 5, 3, 4, and 1. The total teams will be 3. Valid increasing teams is 2, 3, and 4, as you can see in the array. And the valid decreasing teams will be 5, 3, 1, and 5, 4, and 1. And for example number 2, the rating array will be 2, 1, and 3. The total teams is 0 because the array only has 3 numbers and it is not in increasing order or a descending order. And for the third problem from sphere Elijah, the inversion count. Let array A0 and to ms1 be an array of n distinct positive integers. If I is smaller than j and ai is larger than aj, then the pair ij is called inversion of A. Given n and an array A, your task is to find the number of inversions of A. Let me make this clearer. So when an inversion ij is formed, you are looking for a pair of elements based on their positions and values. A pair is valid if the values are decreasing, which means ai is larger than aj. We have hints. If you are currently at index j, how many elements that you have already seen that are larger than your current value? And to return the total number of inversions in the array, I have a hint for this one. So if you use a double nested loop, checking every pair ij, it will take O n squared time complexity. So for large n, this will exceed time limit. So we would suggest you use a Fenwick tree as a frequency counter to count how many larger elements exist in time complexity O log n instead. So this is two examples to classify my explanation. In example number 1, we have array A with value 2, 3, 8, 6, and 1. The output is 5. The inversions that we can count, that is 2, 1, 3, 1, 8, 1, 6, 1, and 8, 6. And in example number 2, the array A is already sorted, so AI is smaller than AJ for all I smaller than J. So the out number of inversions pair are 0. And finally, we come to the last problem from Codeforce, the little girl and maximum sum. So the little girl loves the problems on array queries very much, and then one day she came across a rather well-known problem. You've got an array of n elements. The elements of the array are indexed starting from 1. Also, there are Q queries, where each one is to find the sum of elements indices between Li and Ri. The little girl found the problem rather boring, so she decided to reorder the array elements before replying to the queries in a way that makes the sum of query replies maximum possible. Your task is to find the value of this maximum sum. The instruction is quite long, so I will shorten it and make it clearer to you guys. So the little girl wants to rearrange the array such to get the maximum possible sum of all query results. And we want to return the maximum possible sum of that. And so how can we do this? I have two hints. First one. And the first hint is to maximize the total sum, you need to identify which positions are called high traffic. And a position is high traffic if it is included in many query branches, Li and Ri. And to return the maximum possible sum, if we're calculating frequencies for each index using double loop, it will take O n times Q, which will exceed time limits. So can you use a Fenwick tree to perform range updates in OLOGAN instead? And I have one example to classify my explanation. We have the array nums, which is 5, 2, 3, and 1, with query 1, 2, 2, 3, 1, 3, and 1, 4. So the largest possible sum that I can get from all the query after rearranging the array will be 36. And so how can we rearrange the array that we can get here to get the nums here? So we will count. We see that index 1 is used 3 times in the query array. In this one, and this one. And index 2 is used 4 times in all 4 query. Index 3 is used 3 times, and index 4 is used 1 time. So we will take the largest number and put it at the most used index, which is 5 at index 2. And we repeatedly do that process until we have all queries. And by that, we will place the largest number 5 at index 2, 3 and 2 at index 1 and 3, and 1 at index 4. And the array will be 2, 5, 3, and 1. And then we will take the sum of all queries here. And then we get the maximum possible. And thank you for listening to our presentations about the Fenwick tree.